All right. So before we start our understanding of rotational dynamics, um, we need one quick revision of an aspect of rotational kinematics that is often sometimes ignored in the books to make it very explicit, but this formulae that we going to now talk about will be quite important, right? So what is it? So we've done early in our study something called uniform circular motion. Now that is a nice first exposure to rotational kinematics, but you see things have been made a little easy here, and I want you to note that. So here's a particle and its kinematics. We don't start worrying about why the particle is moving in that fashion. We're interested in quantities like what is the velocity, what is the acceleration, which is kinematics. What we're given is that an object is moving in a circle. Now, uh, this is the xy plane. You have the x-axis and the y-axis. Now, and I just want to emphasize, we are still talking about a single particle. Very important. So, particle rotational kinematics. So, here's this particle which is moving in a circle. Great. And by now, you're convinced that we'll encounter such situations very often. So, the easy part of the fact that it's uniform circular motion is that we never let the radius vary as a function of time. So r is a constant. But it was a little more easy than this. And what was it? It covers equal angle. Okay, angle definitely is a function of time, but it covers equal angles in equal time. In other words, the rate of change of the angle, which in our previous class we've decided to call it omega, which is the rate of change, angular velocity, which is a function of time, is given as a constant. Now these two um, restrictions, that r is a constant and d theta by dt, which is called omega or angular velocity as a function of time, as a constant, are what we call as uniform circular motion. Right. So we did a derivation long ago, and I'm going to now recap what we did in that derivation. So what we did is, look, hello, we do know that a particle is moving in a circle, and can you tell me, and with these restrictions, r is a constant and d theta by dt is a constant. So can you tell me at an instant, any instant of time, so let's say that the particle is here. Can you tell me at that instant of time what is the velocity and what is the acceleration? So this is what we call as the kinematics of uniform circular motion kinematics. And this was indeed a tough problem for us a few weeks ago. And what the answer we got, and perhaps we should now take some time out and try to remember how we got the answer. The answer we got is that, look, this is the velocity, and let's say this is theta at that instant of time. Then the velocity is perpendicular to the so-called radial direction. Okay, so this is the radial direction, and this is perpendicular to the radial direction if the object is moving in the anti-clockwise direction. And we were able to write down the position vector, which I should call it as r. Okay, It's a position vector. We've been using R for position vector. Here we go, the origin R, and since we know this angle, then we found it to be equal to cos of theta plus I, oh my god, how could I miss this, plus sine theta j. And so this was a very accurate and fantastic representation of the position vector. So this is the position, and theta is a function of time with these restrictions for uniform circular motion. What I want to remind you is that we were able to give the answers very neatly in the form of vectors for velocity and acceleration. So just to remind you, V turned out to be R omega, and we all know what omega is. And if I remember correctly, the derivative of cos theta is minus sine theta. Okay, so minus sine theta into omega. Omega is outside. Minus sine theta I plus cos theta j. Okay, so this was our understanding of what is velocity, and this turned out to be very neatly. We were able to write this as cos of 90 plus theta is such a sad way to write it. I think I should have written it as pi by 2 plus theta. Let me just correct it. Pi by 2 plus theta I plus sine of okay, pi by 2 plus theta g. And your trigonometry says that I've got it right. Now this has been interpreted as the magnitude of the velocity is r omega, and the angle that it makes with axis, angle with x-axis, the velocity vector, I'm talking about the velocity vector, is pi by 2 plus 90. Now mind you, this can be very nicely visualized like this. Here I have a object that is moving with uniform circular motion, and I'm able to tell you that it is here, and then I will tell you that the velocity is in this direction, and this is perpendicular to, so the way we interpret this is, look, it's perpendicular to the so-called position vector. This is the position vector r, and this is the velocity vector. So it is tangent to the circle. And the other thing is, we know that mod v is r omega. Okay, so this is your magnitude and this is your direction. Now I think we all remember where we are going. We know the acceleration is at that instant is in the radial direction and towards the center of the circle. So this summarizes all the important results, and maybe I'll you remember this, so let's not waste too much time. And it's minus sine theta I minus cos theta j, and this immediately tells us that it's towards the center. It is directed towards the, this is the direction towards the origin, and this is the magnitude. So we have magnitude of A is equal to r omega square, and the direction is towards the center. Towards the center. There are other ways to say the same thing. It's radial and yeah, towards the center. Radial and towards the center. Okay, so this summarizes. Now, what is it that I'm going to do again? I'm going to redo the whole derivation, because it's so important that you know where the formulas are coming from. It's such a basic derivation, and it's worth revising one more time. In fact, okay, I would like you to do this in this pause the video and work out things with me. So this is a working tutorial. take it as a tutorial, okay, and stay ahead of me and do it on your own once, and then you will remember the formulas forever. So what are we trying to work out? This time we're going to relax and make it just a slightly bit more complicated than uniform circular motion. So we'll continue with r is equal to constant. That means the radius never changes. So it is indeed a circle, but it's not uniform in the sense that r is still a constant. So r is a function of time is still a constant. But this time, let's not assume that omega, which is equal to d theta by dt, which is a function of time, is not a constant. And in fact, it's a function of time. And more importantly, because it's a function of time, d omega by dt is not 0, because it's not a constant. I mean, it can be 0, but then we of course realize it's a constant. But if it is not a constant, we call this as alpha, which is a function of time, which can be constant or it need not be constant. Either way, there's a new thing here called d alpha by dt. I'm sorry, d omega by dt, which is called angular acceleration. So alpha is called angular acceleration, and it is equal to d omega by dt as a function of time. Okay, so alpha t is going to be now into the picture. So the question is, okay, here I have an object. I'm telling you that it's moving in a circle, but it's not uniform circular motion. It's so-called non-uniform circular motion. The other thing that I'm telling you that it's a particle of mass m. It's a particle. Let's not forget that it's a particle. And we have an origin. We have everything. And it's really a kinematic question. Okay, kinematic question. And the question is, hello, can you tell me the, and this is very important now, instantaneous velocity. Okay, that's the velocity at that instant. That's the first question. And of course, what is the instantaneous acceleration? Okay, so we're going to do all this, but we're going to remember it. Now, let me tell you a priori that the answers are going to be pretty much almost the same. And what is that? You will find once again that this is the position vector, which is at a constant r, and this is theta. So that's the instantaneous theta, which changes with time. Now at that instant, this is the direction of the velocity. Okay, so once again it's going to be tangential, and in fact it's almost going to be the same formula. Okay, let me just write it. It's going to be r omega into, yeah, you know the position vector, minus sine theta I plus cos theta j, and of course you can write it like 90 plus theta and so on. Okay, so far so good. So the only difference is that omega is instantaneous omega. It's no longer a constant. So at that instant, if you know what's omega, then you can tell me the velocity at that instant. Great. Now comes the big difference, and we have to not only derive it but remember it. The acceleration at that instant is going to have two components, and the way it's remembered, the way it's recalled is that there is a radial component of the acceleration, and there is also something called the tangential component, which was absent during the uniform circular motion. So there are two components. This is easy to remember the formula. There are two components. One component which is radial, and another component which is along the velocity. It's in this tangential direction, which is called AT, and this is called AR. AR is indeed directed towards the center, and AT will have to calculate. Now here's the first thing. There's no issues with AR. It's also going to be the same as before, R omega square, which is, but the only difference is that omega is a function of time. So at that instant, R omega square is definitely going to give you the radial acceleration. But what is AT? Well, I'll tell you the answer. It's going to be R alpha, which is going to be, R is a constant, mind you, which is going to be R d omega by dt at that instant. Okay, so alpha at that instant. Right, so this is the relationship that we should prove once, because it's so crucial as we go ahead. And of course, I need not tell you that once I give you this, you'll be able to tell me there are two forces. One force towards the center, which is the radial force, and another force which is tangential, which is the tangential force. And the radial force is simply the acceleration multiplied by the mass, and the tangential force is the acceleration multiplied by the mass. I mean, if you want, I can just write it down. F radial is equal to mr, okay, at that instant, is equal to mr omega square at that instant. F tangential at that instant is equal to r alpha at that instant. Oh, mr alpha at that instant. Okay, very good. So basically, the kinematics will give you the formulas for the forces, or vice versa. If you know the forces, you know the accelerations. Right. So how do I get these results? Right. So anyway, let me just summarize the results on how is it different. This time it's a circle, but omega of t is not a constant. Okay, and d omega by dt is alpha, may or may not be a constant. It's called instantaneous angular acceleration. And in terms of these quantities, how do I tell you what is instantaneous alpha velocity and instantaneous acceleration? And this has got two components. One is the radial component, and the other is the tangential component. And these two are, it's obvious, but I better mention it. I mean, these two are perpendicular to each other. A tangential is perpendicular to a radial, and you can handle these vectors. Okay, these are all vectors, right? And this one is easy. It's perpendicular to the position vector, right? And the way we're going to get the formulas are exactly the same as before, and this is what I meant by, please take this as a working tutorial. I'm going to start now, right? So it's fairly important that these kind of computations that I'm doing right now are a little messy maybe 1 month ago, but I think now you'll realize that far from messy, they're pretty much easy to remember. So here's a circle, and here's my particle, and the instantaneous position is given by this angle theta and a radius which is fixed. So I'm going to write the position vector r pretty comfortably. So r is going to be r at that instant cos theta I, so this is your cos theta I plus sine theta g. Okay, now this is r, and if I just do the standard projections, this is your r sine theta, that's the j component, and this is your x component, which is r cos theta. That's the way we've been looking at it. Right, now the question is, what is v and what is a? So let's do this quickly now. Let me just do this. Vx is equal to dx by dt. Remember that x is equal to r cos theta, and this is equal to r minus d theta by dt. This is the difficult part, I would say. This is a chain rule into sine theta. This is the difficult part, and we still haven't done this in the class in calculus, so you have to accept this one. And this is being called as omega at that instant. I'm just writing it here. Omega is equal to d theta by dt at that instant t. Okay, now this helps us to write this as minus r omega at that instant into sine theta at that instant. So this is your Vx, and therefore what is Vy is equal to, same thing. I'm not going to now repeat. It's a tutorial. You can pause and work it out on your own. I think it's r omega d cos theta at that instant. Now the whole thing is combined, and we write this as Vxi plus Vyj, and this is the velocity, and this is equal to, I'm just writing it a little compactly, it's minus sine theta I plus cos theta j. So it looks exactly like the previous case, except like I said, omega is not a constant. So v is, and by the same reason, it is, the direction is perpendicular to the position vector. So this is the position vector, and we can easily convince you that the velocity vector is perpendicular to the position vector. So I'm just going to write it here. R omega is the magnitude minus sine theta I plus cos theta j is a unit vector that is perpendicular to the position vector, and therefore mod v is equal to r, I think I should be more careful, omega t is a function of time, mind you, and the direction is pretty obvious. Alright, now we'll just continue with the same thing, and this time things start getting a little messy, right? So I'm just going to do the, okay, here it is. A is equal to, okay, I'll just find ax and ay, right? And you know what ax and ay is. It's dvx by dt, and we already know what vx is. What is vx? I think it's r omega, now it's not a constant, into minus, I think, cos t, one second, sine t, sorry, sine theta. Okay, right. So, and then what is vy? Vy is dvy by dt, and this vy is equal to r omega cos theta. Right. So now this is the messy part, and we have to do it. So why is it messy? Because we've got two functions of time. Okay, so this is also a function of time, and this is also a function of time. If in the previous case this was a constant, so it was very easy. And when you have a product like this, here's the rule. So let me write only ax. Don't worry about r, so let's not worry about r, it's a constant. Now the product rule which you're going to learn is that you let the first function as it is, okay, and multiply it by the derivative of the second function, which happens to be cos theta, into d theta by dt. So this is the really not so easy step, right? But you have to remember this chain rule now, plus sine theta, okay, into t into the derivative of this, which by the way is alpha. So I'm going to this is a quick step which is not worth writing it in a complicated manner, because you all know that d omega by dt by definition is alpha. So let's not delay this step, and we're done basically, except for the fact that it looks a little daunting. And remember that this is ax, so maybe it's not as bad as I made it out to be. And so using this, please try to work out on your own ay and then try to see if it matches with my answer. It should, I guess. Omega t into minus sine theta, making sense, I think, into minus sine theta into d theta by dt. And remember that this itself is omega, and this itself is also omega, and then plus cos theta of t into alpha. Right, so things don't look so bad, and this is your ay and this is your ax. So let me just write ax as minus r times omega square. Okay, this omega is being multiplied by this omega. Omega square cos of theta t, okay, plus alpha times sine theta t. And this one will be written as r times minus omega square omega t square sine theta d plus alpha t cos of theta t, okay, alpha times cos of theta t. Right, I hope I haven't made any mistake. I still don't know, I might discover it, but you are also working along with me. So this is your ax and this is your ay. I can try to see if I can make a quick check. Looks okay to me, but we'll have to just, yeah, it seems okay actually. Okay, so now I have it or I can just refer back to it, but I'm going to write it now, arrange it. So the last step is as important as the entire derivation. A rearrangement is important. So I'm going to write this now as a is equal to axi plus ayj, which you will readily agree. So now I have ax. I'm going to write it as so this, just to tell you, this whole thing has to be multiplied by I, and this whole thing has to be multiplied by j. So watch what I'm going to do now. I'm going to club this term with this term. And why? Because they've got a minus r omega square. Okay, I'm going to club this term with this term because they've got alphas with them, and then see what happens, because I'm in for a pleasant surprise, you're in for a pleasant surprise. So watch, when I club these two terms and these two terms, what happens? You get minus r omega at that instant whole square minus r omega square cos of theta t I plus plus these guys, which are very similar in nature, but there is a minus sign and there is a sine theta, but it's j. So I'm going to write it as plus sine theta tg. And so I've got two terms here. There are two more terms which have alpha in them, but this alpha has got I and this alpha term with cos theta has got j. So I'm going to write it as plus r alpha t. You will see that there is a r here and an r here, and therefore this will be minus sine theta because there's a minus sign here, and this will be plus, which is cos theta. So it's going to be minus sine theta I plus cos theta tg. And we're done. We are really done big time. So this is your acceleration. Now one quickly realizes that, like before, this is the position vector. If this is the position vector, then with a minus sign, it's indeed towards the center. So therefore, this is a unit vector in the tangent radial direction. So how should I write it? A unit vector in the radial direction, and this is the magnitude of the acceleration in the radial direction. So this, now I don't want to repeat the same thing again, is basically in the direction of velocity, which is basically the tangential direction. So this is a unit vector in the tangential direction. We've looked at it so many times that you will immediately recognize this as a unit vector in the tangential direction, and this is the magnitude of the acceleration in the tangential direction, and therefore it can be written as the radial direction acceleration into the unit vector towards this, or whatever you want to call it. Okay, there is a minus sign, so AR plus A tangential, and in the unit vector in the tangential direction. And here you see that the magnitude of the tangential acceleration is r alpha instantaneous, and the magnitude of the radial acceleration is minus r omega square. That's towards the center. So once again, our unit vectors have really helped us to visualize this. So just to summarize this in another way, there is a object moving in a circle. Right now it happens to be here, so this is the position vector, and the radius is constant. The velocity at that instant is definitely in the tangential direction, and instantaneous velocity is definitely in the tangential direction, and the magnitude of the velocity is r omega t, which is omega at that instant, the angular velocity at that instant. And now comes the big thing that we've achieved in this class, and that is the acceleration. The acceleration has got two components. One towards the center of the circle, which is very similar to we're calling it magnitude of the radial acceleration, and it's towards the center. It's r omega t square. And by the way, you can continue to call this mod v square by r, as you can quickly check from here. No big deal here. But the real big achievement is A tangential. So A tangential is equal to, as you can see from here, R alpha. Now this is a very big relationship, and this is only because we're no longer assuming that omega is a constant. Alright, so but remember that the radius is still a constant. So we've derived this relationship and we're going to memorize it. So what is it? In a circular motion, of a particle with constant radius, the velocity is perpendicular to the position vector and is equal to r omega. The magnitude is r omega. Okay, omega at that instant. And the fact that it is perpendicular to the position vector is given by this, which is nothing but cos of 90 plus theta plus cos of theta g, theta at that instant, theta at that instant. And the way to say it is mod omega is equal to, mod v is equal to r omega at that instant, and the direction is clear. What is interesting is acceleration is having a component, two components, a tangential component towards the center of the circle, whose magnitude is radial component towards the center of the circle, whose magnitude happens to be minus r, whatever you want to call it. Okay, magnitude happens towards the center because we have already said it's towards the center of the circle, whose magnitude at that instant is r omega squared. And this can also be written as the instantaneous velocity square by r. But the new thing we have discovered is that AT is not 0. In fact, it is equal to r times alpha t, which is the same thing. Magnitude is r times alpha t, and it's along the tangential direction. And this is equal to, which is the same thing as r times d omega by dt at that instant. And what we realize is that in uniform circular motion, this quantity is 0 because alpha is 0. That is because omega is a constant and d omega by dt is 0. So this is 0. Alpha is 0. So alpha is equal to 0 for uniform circular motion. And that is why everything else is fine except for this tangential component, which now appears. Okay, so why have we done all this? Because we are going to get into particles which are performing circular motion, that is constant radius, but omega is not constant, implies alpha not equal to 0, and alpha can be a constant or alpha can be a function of time. Okay, both of these are fine with us, and the formulas we have derived are catering to these two cases, which are an important case. So that concludes the rotational kinematics that we need, and we are ready to do pure rotation in the next upload. And this particular video, I hope, has been clear enough. I'm not 100% sure that it's very clear, but believe me, it's very easy, and you don't have to worry too much about this. Just work it out on your own once, and you'll be fine.